Okay, guys, on the forces, Google Classroom unit, I do have it said lecture 1. This will be listed as lecture 2. So lecture 1 was over Newton's first law of motion. Then we did that mini lab, the bowling ball inertia lab, and then we'll do Newton's second law, which is really just a formula. It's just putting into an equation when you put force on something. How that affects a mass and how it makes it accelerate. So it's really just a formula. Then Newton's third law, which will start after that, will be more project based, and that's for every action there's the equal opposite reaction. Okay, so everybody turn to Newton's second law of motion in their packet. Okay, so you're going to learn some new terminology with our already known scalar and vector nomenclature. Okay, so Newton's second law of motion. The main idea to Newton's theories is that forces cause accelerations. Forces cause, I'm just going to do A hat, accelerations, okay, as opposed to velocities. And no force is needed to keep an object moving at a constant velocity. Moving at a constant velocity. Okay. And so now we're going to talk about those factors. So we already talked about force, capital F hat. So it has a hat, it's a vector quantity. We know acceleration from last unit, A hat, vector quantity. And then we're going to learn how it always has to do with some sort of mass, okay? Mass does not have a hat, so it is a scalar quantity. We're also going to learn that these pretty much have set units, okay? So, in fact, the acceleration, A hat, is proportional to the total force F hat net. Proportional to the total force, okay. And so net, just like in other math classes, means the total acting upon it. And IPC, you guys had Coach K. When I taught IPC, we would always look at free body diagrams, which we are going to look at in here, and you look at all the forces acting upon an object. So it's not just one force, it's like all the forces. So we have acceleration is proportional to force. We're going to learn about this new thing called proportional, okay? This was counterintuitive to most, but this can easily be demonstrated. Imagine a mass on a table connected by a string to a mass hanging off the edge of the table. What happens? What happens when the mass hanging off the edge of the table is doubled? Okay, so proportional. Does anybody know what proportional means? A lot of times we use it when it comes to like ourselves, like, oh, she looks pretty proportional, or that looks pretty proportional. Equal. Yeah, goes together. That does not look proportional. Okay, so proportional means goes with. Okay, and when it comes to numbers, if you say something is proportional, it means if one increases, the other increases. If one decreases, the other decreases. So acceleration is proportional to force. Let's switch it. Force is proportional to acceleration. Ready? The more force I push Sammy, the faster she accelerates. Okay? Easy. Okay? When you just read it up there, you're like, oh, Miss Feist, do I have to memorize this? But think about it. The more force you push on an object, the more you cause it to accelerate. And we're not talking about velocities, we're talking about accelerations. Okay. So, if you have a mass hanging off a table and then you double it, what happens? The acceleration doubles, okay? So that last question, what happens? What happens when a mass hanging off the edge of the table is doubled? Acceleration doubles. I'm just going to do A hat doubles. Okay. Okay, so here is our new sign for proportional. Y'all, I just kind of draw it like that. Have y'all seen that symbol before? Kind of looks like the fish they put on, like, the Jesus fish, okay. So acceleration is proportional to force. If one goes up, the other one goes up. If one goes down, the other one goes down, okay. So we read it, acceleration is proportional to force. This means if one is increased, the other one will increase by the same factor. So it's proportional, it's exactly proportional, okay? So that's when we said what happens if the mass is doubled, the acceleration doubles by the same factor, okay? So if you read something, acceleration is inversely proportional to mass, this means that if one is increased, then the other will decrease by the same factor, and it's the same for force. So ready? We have acceleration is proportional, but when you put it in the denominator, it means inversely, okay? Some people might even write it as acceleration is inversely proportional to mass, okay? But this one I like a lot because you're still using the proportional symbol, but whenever anything is now in the denominator with the 1 on top, it's inversely. So that makes sense because when I'm way bigger and you push on me, do I accelerate that much? No, but when I'm smaller, you push on me and I accelerate a lot. So mass is inversely proportional to acceleration and force, and we'll draw that in a little bit. Good. And when we put them all together, acceleration is proportional to the force exerted upon it divided by its mass. If the mass is given in kilograms and the acceleration is in meters per second squared, the proportionality can be written as an equality, okay? And it's going to be the force is in newtons. Okay, we'll talk about that. So they're telling us acceleration is force divided by mass. That's all they're doing. They're telling us that's our formula. It is proportional, but this is where they're coming up with their formula. So let's write that down here. Okay. Is y'all's box gray? Mine's not that gray. Okay. So they're telling us acceleration is force, capital F hat, all over mass, okay? But in IPC, when I teach it, and also when it's just another way to do it, but we call Newton's second law of motion F equals ma. I'll just write or. F equals ma. Okay? This shows a better proportionality. This one is what we learned in middle school, and like I said, when I taught IPC, it was F equals ma. The force you put into an object depends on its mass and how much you want it to accelerate, okay? And then lastly on here, let's put down the units so we can look back to. So units, we were just told that the units for acceleration, just like last unit, were meters per second squared. We were told mass is going to be in kilograms, and that's how it's going to be on the worksheet for today. Okay, and now force, y'all, it's going to be in newtons, although whenever we do the math, I think it's going to be acceleration over mass, okay? So it's gonna look like it's meters per second squared per kilogram, but really, whenever you're looking at force, the units are newtons. Okay. Okay. An object's acceleration is determined by the net force exerted on it by its environment and by the object's mass. So it's literally just putting acceleration, force, and mass in the same sentence. The direction of the acceleration is the same as the direction of the net force. That's a really good one to know. The direction of the acceleration is the same as the direction of the net force. So when we do problems, whenever they give you a direction for one, it should be the same for the other. So quantitatively, the acceleration is proportional to the net force divided by the mass, okay? They just want us to reiterate the formula again. Acceleration is proportional to the net force divided by the mass, to the force divided by the mass. Okay, so here is something that we can draw to kind of help us. I kind of like this because it does give you a visual if you're a visual learner. So I'm going to divide this into fours. Okay. And so first two, these two are going to go together. Okay, and I'm going to draw two masses that are approximately the same. I think they're the same. Okay. And I'm going to put an M inside of them for a mass, okay? And what you're going to learn is that when we're looking at all the forces on an object, we're doing something called a free body diagram. We're going to learn it in maybe a few classes. It's where if I push an object, do not do this. You don't put an arrow up to the object and be like, oh, I pushed that object. You actually have a dot in the center, almost like the object's like core, okay? And you pull that object in the direction where the force took it, okay? So on this first mass, I'm gonna write a small force, okay? And on this second object, a large force, and on this second one, I'm gonna do a small force. Okay, same mass, different size forces, okay? I might even do force LG for large, force small, okay? Tell me about the accelerations. We'll call this one 1, we'll call this one 2. Tell me about the acceleration for 1. Is it going to be a large acceleration or a small acceleration? You have a mass with a large force pushed onto it. Large acceleration. What about for number 2? You have a small force. Small acceleration. So ready? We're going to say about the same proportionality right here. Acceleration. That was pretty large. Okay? And then we're going to have about the same proportional as this. For acceleration, small. Okay? So draw that, and then we're going to write the proportionalities. Okay, so if I have two objects and I push one with a large force, it's going to get a large acceleration because force and acceleration are proportional. Ready? I'm going to do that in a different color to summarize it. So this is showing that force. Okay. Oh, what's going on? That force is proportional to acceleration. Okay? Now, I'm I'm gonna come over here, and I'm gonna do our second formula, which has to do with differences in mass. I'm gonna do a big mass right here, and about the same mass as this one right here. Okay, so this will be kind of like box 3 and box 4, they go together. Okay, they're each gonna have a center of the mass, okay? Now for these, I'm gonna do the same force. I will call these forces, because they're about this, I'll just say small. Okay. Okay, which one is going to accelerate more, 3 or 4?
4.
Why?
Because it's smaller.
Good. So you have a greater acceleration because of a smaller mass. That is inversely proportional. Good. So I'm going to draw that. This is going to have a small acceleration. This is going to have a greater acceleration. I'll just do LG, okay? Because this one demonstrates how, and it's force and acceleration, both of them this applies to. We learned it as acceleration is proportional inversely to mass. Make sure you're copying these. If we do a CBA, y'all may be able to use your packets, and as long as you're putting your notes in your packets, I think y'all will do good. Okay. Last one is just an example. Okay. A 5 kilogram wooden crate experiences a force of 6.1 newtons west. Determine the acceleration. Okay. So they gave kilograms, that's a mass. They gave us a mass. The mass of 5.7 kilograms. Okay. They gave us a force of 6.1 newtons west. And they gave us, they said acceleration. We do not know. They left it blank. So this is what we have to solve for. Okay, one thing I didn't do that I did for the other class is back, and we could do it here, you could do it wherever, on the previous page. You could even do it up here or where the previous page had like a darker box. Okay, you could fill in this triangle, so I'll do it right here. Just like we did speed, okay? But remember, 2 things have to be in the denominator, 1 thing has to be in the numerator. So ready? They taught us acceleration is force over mass, or I told you the one that I liked was F equals ma. Okay? How do I fill that in my triangle? What do I put on top? Yes, so y'all, whatever was on your numerator, that goes on your numerator right here. And then look at these 2 right across from each other, they're on your denominator. Awesome.
That's all the time?
Well, yeah, as long as you have one of these formulas to put in. So now if I don't know acceleration, I block that out. So when I solve for it, it should just be force over mass. So my acceleration equals my force, 6.1 newtons west, all over 5.7 kilograms. my acceleration equals. Okay, when I do 6.1 divided by 5.7, I get 1.1, okay? Now, here are the units that I was talking about before. Newtons per kilogram. If you would put acceleration as 1.1 Newton per kilogram west, you're not technically wrong, but there's a conversion. Newtons per kilogram is meters per second squared. Then we carry down the direction west. So, if you memorize, okay, mass is in kilograms, force, Newton's 3 laws of motion is in newtons, and acceleration is meters per second squared, that's the units for all of them. Okay, so we are going to get a worksheet now. Is it for this week or last week? This week. Oh yeah, honors quiz, Pam.
That was scary.
Okay, put your name on it, fill in the triangle at the top, that way you have it while you're doing this. Okay, for this worksheet, I would like you, just because I want to see what you're filling in and see if anybody's having problems where they're getting stuck at. For question number 1, for example, I don't really care how you do it, but like I do want you to list all 3 variables and fill them in, and then I'm gonna look at your work. You could fill in that 3rd variable here, you could even put it as an X, whatever, and then remember, box in your answers. So for number 1, how much force is needed? So that is my X, I don't know force, to accelerate a 66 kilogram mass, 66 kilogram skier at 2 meters per second squared, 2 meters per second squared, okay? You have your triangle up there, and it's okay if you just cross off on your triangle and then you solve down here. So you should be solving for force equals, okay? If I have my triangle up here, we already said force is up here, mass acceleration. Okay, I don't know my force, so when I cover my force, it's just mass times acceleration. So force is 66 kilograms times 2 meters per second squared, 2 meters per second squared. Okay, they did not give us a direction, so if there is no direction, and I actually think this worksheet, I didn't love it because there were no directions. It's just focusing on the calculations. So just focus on the calculations. Okay, so when you solve it, y'all, make sure you have what you're solving for force. What's 66 times 22?
What, 22 times 2?
Times 2, sorry. 132. Okay, I think so. 132. What's our new unit for force? Newtons. So make sure you have that boxed in.